Welcome to the lesson for section 1.6 on the absolute value function. By the end of the lesson, you'll be expected to graph absolute value functions, solve absolute value equations, and solve absolute value inequalities. The absolute function can be defined in a piecewise manner. If you recall, we did this in section 1.2. And the definition is as follows. We have f of x equals the absolute value of x equals x if our value of x is greater than or equal to 0, or negative x if x is less than 0. Now let's look at some examples. Example 1, distance. Draw a graph on a number line that depicts all values of x that are within and including a distance of 3 from the number 0. So let's start by sketching in some key places on our number line. We are looking for all values of x that are within and include a distance of 3 from the number 0. So let's start with some positive values here and ask yourself, is the number 1 within 3 units from 0? Let's count. This is 1 unit. So this number is definitely within 3 units of 0, so this is definitely going to be included on my graph. What about the number 2? Is this within a distance of 3? Let's figure that out. 1, 2. It is a distance of 2 units. So it is definitely within a distance of 3 from the number 0. So this can also be included on our graph. Now let's ask ourselves, is the number 3 a distance of 3 from 0? One, 2, 3. It is at least a distance of 3 from the number 0, so it's also included on our graph. And we want to include 3. You notice this says including, so I'm going to make this a nice closed dot. Now let's look at the negative side. And let's ask ourselves, is the number negative 1 within 3 units or a distance of 3 from the number 0? This is 1 unit, so that's going to be on our graph. But if you notice the number 2, here's another unit, so we have a total of 2 units. This will also be included on our graph. Now let's look at the number 3. 1, 2, 3. It is within 3 units of 0, so we're going to include all of these values in our graph. And since we're including the distance of 3, instead of putting an open dot, we are going to fill this in as a closed dot. And there is our graph. Now this can be interpreted as the absolute value of x is less than or equal to 3. Let's go ahead and continue the example. Draw a graph on a number line that depicts all values of x that are within and including a distance of 3 from the number 2. There are my values. And now we want a distance of 3 from the number 2. So here's the number 2. And let's see what values are within a distance of 3. A distance of 3. You can go 1, 2, 3. All of those values are within a distance of 3 from the number 2, so they're included on our graph. And since this specifies that we want to include the value that is exactly a distance of 3, in this case it's 5, we're going to draw a dot and fill it in to be a closed dot, since that implies inclusion. Now what about on the left side of the value of 2? Let's go ahead and figure out what numbers are a distance 3 from the left of the value 2. 1, 2, 3. So all of these are included on our graph. And again, this specifies including a distance of 3. Since -1 is exactly 3 units away, we're going to fill this in with a circle that is completely filled in. And there it is. There's our graph that depicts all values of x that are within and include a distance of 3 from the number 2. So how can we interpret this algebraically? Let's look at either endpoint. Let's start with x is greater than or equal to -1, and x is less than or equal to 5. Here, this represents this value. We want the values that are greater than or equal to -1, and here we want the values that are less than or equal to 5. Let's rewrite these. I know I want to have a 2 somewhere in here, so let's subtract 2 from both sides of each inequality. That means this becomes x minus 2 is greater than or equal to -1 minus 2, and x minus 2 is less than or equal to 5 minus 2. If you notice, all I did was subtract 2 from each side of both inequalities. And now we can rewrite this as x minus 2 is greater than or equal to -3, and x minus 2 is less than or equal to 3. If you notice, here -1 minus 2 became -3, and 5 minus 2 became +3. This, by definition, is the absolute value of x minus 2 is less than or equal to 3. Since we want the positive case, that is x minus 2 is less than or equal to 3, and then when we look at our negative case, if we're starting here and going backwards, we would write this as x minus 2 is greater than or equal to -3. We flip the inequality there. So this is how it can be interpreted as an absolute value. Notice, originally we had the absolute value of x is less than or equal to 3, and now we have the absolute value of x minus 2 is less than or equal to 3. What did that do to our graph? Originally we were centered here at 0. Now we're centered here at 2. If you notice, the graph was shifted 2 units to the right. This coincides with what you've already learned about graphing functions. Let's look at example 2. Graphing the absolute value function. The graph of f of x equals the absolute value of x can be manipulated with the techniques of the previous chapter. Below, sketch f of x, sketch g of x equals negative f of x plus 2, and sketch h of x equals f of x plus 2 plus 2. So if you notice here, our original absolute value will become negative. That's a vertical flip, so a flip with respect to the x-axis, and then it's going to be shifted up 2 units. The graph of h of x is going to be shifted, so notice here we shifted 2 units to the right, so here we're going to shift 2 units to the 1, 2 to the left, and then we're going to raise this up by 2 as well. So let's go ahead and sketch f of x in green. And the absolute value of x, if you remember, let's sketch a little table, it'll help. So the absolute value of negative 3 is going to be positive 3. The absolute value of negative 2 is just 2. The absolute value of negative 1 is just 1. So 0 and then 1. So first I go to the point negative 2 and up 2. And that's a dot. Negative 1 and then up 1. 0, 0. Here I can go 1 to the right and 1 up to get a point there. And then same here. 2 to the right, 2 up for this point here. And now go ahead and connect the dots. And this is the graph of f of x. Now that we have the graph of f of x completed, let's use the manipulations we've already learned, the translations and transformations of graphs, to graph out both g of x and h of x. Now let's go ahead and sketch our graph. So for g of x, if you notice, we need to flip this graph upside down, so it should be in this direction, and then raise it by 2. So this here, in the very pale blue, is just the graph of negative f of x. So now I need to raise this entire graph up 2 units. That would be 1, 2. Same on this side of the graph. Every point should be 2 above the original line, and now we can connect these dots. And here we have the graph of g of x. So let's do the same thing for the graph of h. So first we want to shift this original graph 1, 2 units to the left. So originally we were here at 0, 0, so this is going to go 1, 2, 1, 2. It should be here. And let's do this again in a lighter color. It's shifting over 2 units. And so on with every point. And let's go ahead and connect these dots. So this is just the graph of f of x plus 2. Now we want to shift our graph 2 units up. Since we're adding to here, we want to shift 2 units up. Let's go ahead and do that. So this point would end up here. This point would end up here. And our new graph, squished in right here at the top, would look like this. And here is our graph of h of x. Example 3. Find all the values of x for which f of x equals 0 for the function f of x equals the absolute value of x plus 1 minus 3. So we're going to use this open space here to solve this algebraically, and then we're going to use a graph to solve this as well. F of x equals absolute value of x plus 1 minus 3, and I want to solve this for when f of x equals 0. So wherever I see an f of x, I'm going to replace that with a 0. That's right here. This becomes 0. If 0 equals the absolute value of x plus 1 minus 3. Let's go ahead and add 3 to both sides. And now I have 3 equals the absolute value of x plus 1. I'm going to want a positive case and a negative case. So here's my positive case, x plus 1 equals 3. And my negative case, x plus 1 equals negative 3. So when you get to this point, that is when your absolute value is isolated on one side of the equality, you want to split it into a positive case and a negative case. Now we can finish solving both of these as we would, or as we have in the past. So subtract 1 from both sides to get x equals 2. And let's do the same here, minus 1. end up with x equals -4. Now let's go ahead and graph f of x. Again, I know I shifted this 1 to the left and then down 3. And if you remember, the absolute value graph always starts off here at the origin. So this point is the one that got shifted 1 to the left and then down 3. And there is no number on the outside to stretch this or compress this. So I can go ahead and just draw the rest of my line. And this is f of x. So we want to know when f of x is equal to 0. That would be right along the x-axis. So let's highlight these x-intercepts in red. Here's one. This occurs at the point -4, 0. And here's our other point, which occurs at 2, 0. If you notice, these are precisely the solutions we obtained of x equals 2 and x equals -4. So when you're solving a problem like this graphically, you're asking yourself, when does this function intersect this function? So we intersected this absolute value function with the line y equals 0, which is simply the x-axis to get x equals 2 and x equals -4, which represents the two x-intercepts of 2, 0 and -4, 0 on a graph. Now let's do this again for example 4. Example 4, solving absolute value equations. Given f of x equals absolute value of x minus 2 plus 3, solve f of x equals 4 and f of x equals 1. So let's start by doing this algebraically. And we want to solve two different inequalities. I want to solve absolute value of x minus 2 plus 3 equals 4. And I also want to solve the absolute value of x minus 2 plus 3 equals 1. So let's go ahead and subtract 3 from both sides. And we end up with the absolute value of x minus 2 equals 1. So now I want my positive case, x minus 2 equals 1. So this is the positive case. And then I want my negative case, x minus 2 equals -1. From here, I just add 2 to both sides of this inequality to get x equals 3. And then I can also add 2 to obtain x equals +1. Now let's go ahead and solve our second equation. Let's start again by subtracting 3 from both sides to end up with x minus 2 equals -2. And before we continue and try to split this into a positive case and negative case, let's ask ourselves a quick question. Can an absolute value ever be negative? So this example, we have no solution. Now let's look at these graphically. Now let's go ahead and draw our function. So again, remember, typically our absolute value function would start here at the origin and go off in two directions. This one is shifted 2 to the right, so this point will go 1, 2, and then shift it up 3. So this point needs to shift 1, 2, and up 1, 2, 3 to here. So here we have the graph of f of x. Now let's go ahead and sketch out a line for y equals 4 and y equals 1. So I'm going to have these colors match up. So let's go sketch out the line of y equals 4. That is a horizontal line. And let's also draw the line of y equals 1. see what we notice. Let's start by looking at this case where we found no solution when we set our original equation equal to 1. Here's the line y equals 1, and here's our function. Does this function ever cross this line? It is really clear visually that these two will never meet. This is why this has no solutions. Now let's look at the first case where we let everything, our equation, our function, equal to 4. And we solved and got the solution of x equals 3 and x equals 1. And let's find those on our graph. I'm going to highlight those in red. If you notice, these occur at the same places our absolute value function intersects our horizontal line. That is at the ordered pair 3, 4, and here at the ordered pair 1, 4. Our x value is 1, the solution of x equals 1, and this x value here is 3, which coincides with this solution of x equals 3. Example 5, solving an absolute value inequality. If you have version 2 or above of the guided notes, this change should be done for you. So let's start off by writing out negative 2 times the absolute value of x plus 4 plus 7 is less than or equal to 3. Subtract 7 from both sides, and we end up with negative 2 times the absolute value of x plus 4 is less than or equal to negative 4. And before you write out no solution because you see there's a negative here, pause real fast and notice this is a negative as well. So we can divide both sides by negative 2. And remember, because we just divided by a negative, we need to change the direction of our inequality. So we did have a less than or equal to. Now we have greater than or equal to negative 4 divided by negative 2. This leaves us with the absolute value of x plus 4 is greater than or equal to 2. So let's go ahead and look at our positive case, which is x plus 4 is greater than or equal to 2, and our negative case, which is x plus 4, and I'm going to have a negative 2 on this side since I want this to be negative, but again, I need to flip my inequality. So now I want to subtract 4 from both sides, and I end up with x is greater than or equal to negative 2. And then let's subtract 4 here, end up with x is less than or equal to negative 6. So again, this was a crucial step right here where you flipped the inequality after dividing. You'd have the wrong directions here if you didn't. And then we need our positive case. This is another crucial step, and the direction of the inequality stays the same. And our negative case, where the direction of our inequality changes. Now let's see what this looks like graphically. Our original absolute value graph has a vertex here at the origin, which is 0, 0. This graph is going to be shifted to the left 4. That's 1, 2, 3, 4, and then up 7 to here. So our vertex is going to be here at negative 4, positive 7. And then if you also notice, we have this negative 2 on the outside. So in gray, really quickly, I'm going to pretend that 2 isn't there, but the negative is. So here in gray, if you notice, I have the graph. Let's call this g of x equals negative absolute value of x plus 4 plus 7. Let's see what happens when we include this multiplication by 2. So I'm going to highlight some key points here. So those 4 should be enough. Now let's create a little table. So we have x, g of x, and f of x. And again, g of x is here in gray. So let's see what happens at -6, -5, -4, -3, and -2. So we know that g of x has the following points. So at -6, we have 5. At -5, we have 6. At -4, we have our vertex, which is -4, 7. And then we have -3, 6, and -2, 5. So go ahead and pull out a graphing calculator or just a standard calculator as I have done. And let's see what happens when we multiply this -2. So let's start here with a -6. So let's add on our calculators -6 plus 4. We end up with a -2. So now I want the absolute value. I want -2 times the absolute value of -2 plus 7. Well, what is the absolute value of -2? This is simply going to be a +2. So this will be -2 times 2 plus 7. And to obtain 3. So if you notice, you don't need a fancy graphing calculator to do this. You can do these in several steps and get the same answer. Now let's, for the next one, use a function, the absolute value function, on the graphing calculator. So I'm going to type in -2 times, and then go to the math button here, and I want to get to my number menu by scrolling to the right. And here at number 1, we have absolute value. I'm going to hit enter, and then inside I'm going to type in -5 to represent this value here, this input. I'm going to add 4 to that, because in our function we add 4. Then I need to get out of this absolute value and go plus 7. And that's this part right here. And let's go ahead and hit enter and see what happens. I end up with 5. Please pause the video and fill in the remainder of this table. Okay, now that your table is filled in, let's go ahead and plot our ordered pairs. So I have -6, +3, -5, +5, 4, +7, -3, +5, and -2, +3. And then we can connect the dots. Finally, let's go ahead and graph y equals 3. Now we can use our graph to verify our solutions. So our first solution is x has to be greater than or equal to -2. Well, what happens when x is greater than or equal to -2? We're right here. So it's in this region. We're right here. So it is in this region that this function is less than or equal to 3. You notice, as long as we keep going in this direction, we'll always be less than 3. At -2, we are exactly at 3. You can also verify this solution. X is less than or equal to -6. And in this case, we go out to the left from -6. As long as we are less than -6, this function will meet the criteria of being less than or equal to 3. So here we have our algebraic solution, and here we have our graphical solution. This concludes section 1.6.